Hello, my name is Colin. I'm a PhD student at Stanford University, but this is quite the multi-university effort. As you can see, where I have the privilege of working with this team of fantastic researchers. So I'll begin with an analogy because I think it's a helpful way to understand the work that we're trying to do here. A pentimento is the presence or reemergence of an early image which has since been painted over. For example, if we look at Rembrandt's An Old Man in a Military Costume, to the naked eye, it looks fairly unsuspecting. But when we apply X-ray imaging techniques, we can reveal artifacts of a previous image that has since been painted over. So why do artists do this? Well, they could be reusing an old canvas, they could be covering up some old mistakes, or they could be trying to censor something that was previously on the canvas. Now we've become interested in what we call digital pentimenti. And instead of recovering artifacts of old paintings, we're recovering artifacts of old digital data. And this could be any sort of personal information. It could be machine learning weights or cryptographic keys. So how and why do these digital pentimenti emerge? Well, as digital designers, we have a very idealized view of digital logic. So here's a NOT gate that takes some input and gives you the opposite value as an output. But really this looks more like this. You have a PMOS and an NMOS transistor to create that inverter. But really the transistor is not the most atomic unit here. Transistors are fairly complicated beasts. And so here's a cross-sectional view of a PMOS transistor in the off state. And then when a low charge is applied to the gate, current is allowed to flow through the transistor. But transistors are imperfect and they begin to degrade over time. One possible way this PMOS transistor can degrade is through a process called negative bias temperature instability, in which holes become trapped in the gate dielectric of the device. And this changes the threshold voltage of the transistor, which, as we'll see, forms a pentimenti. So, how does a pentimenti emerge from this bias temperature instability effect? Well, if we return to our idealized view of an inverter, if a 0 value was inputted into the inverter, that means a 1 value will come out as the output. That 1 value will stress the PMOS transistor in the inverter. And as that stress is left to sit for a long period of time, holes will become trapped in the gate dielectric of the device, which will change the threshold voltage of the transistor, which will emerge as a timing deviation in how quickly this inverter is capable of switching. Now, a similar process emerges if the input to the inverter were a 1 and the output of the inverter would be a 0. That would stress the NMOS device, in which case we would see an analogous effect for NMOS transistors called positive bias temperature instability, where instead of holes becoming trapped in the gate dielectric, electrons become trapped in the gate dielectric. And this expresses similarly as a timing deviation in the nominal timing delay of the inverter. And these bias temperature instability effects are creating a long-term measurable timing difference, and that is our pentimenti. And so if we were able to precisely measure the timing difference or the timing through these digital components, we can determine the previous logical value that they held. And that's the fundamental premise of our work. Now, we're particularly interested in this with regards to cloud resident field programmable gate arrays. We see them as a pretty high-risk target because you have consecutive users who have the expectation of total isolation between previous and future users. Bias temperature instability effects have previously been measured on local FPGAs using both conventional sensors like an oscilloscope and with programmable logic sensors. And it is these programmable logic sensors that enable remote attack and make this cloud model so interesting. Though these programmable logic sensors have never been applied to the cloud, and most of the bias temperature instability work has focused more on reliability testing or searching for long-term data remnants. So you know if you can safely sell your FPGA to a third party without revealing data. And so from that, our cloud FPGA threat model emerges, where there's some data center with an FPGA instance, and some user rents that cloud FPGA instance that instantiates some piece of sensitive information, and that sensitive information is distributed throughout the design using the FPGA routing. The user then performs computation for a number of hours, at which point their computation is complete and they can relinquish the device back into the cloud data center. At this point, an attacker rents that same FPGA after the previous user has relinquished it, measures the timing delay through the routing which previously contained that sensitive data. Again, that sensitive data is completely logically not present anymore. They're just measuring the timing through the route which previously held that sensitive data. And from that timing information, they can extract what that previous value was through the Pentimento. Now, we leverage a timing to digital converter in our work. I'm not going to focus on that. I think there's been 3 introductions to TDCs already, so you guys know it by now. I'll just note that it's undetectable, so we can upload it to cloud providers, and it allows us to measure the timing delay through routing, which allows us to expose this Pentimento. Now, to experimentally validate some of these spots, we performed a local experiment where we instantiated the core on an FPGA locally, and that core contains some sensitive data, and that sensitive data is dispersed throughout the design using the FPGA routing. We then let that FPGA sit in an oven at a slightly elevated temperature to bake for a period of time. Then we load the design with our time digital converters and measure the delay through those routes which previously held, the sensitive data, an AES key, for example. Then we repeat this process over and over again to study how the timing delay changes over time through these sensitive routes based on what value is actually being held in that sensitive route. And what we find is that when we look at very long routes, so 10,000 picosecond delay routes, that immediately starting at hour 0, the timing delay, how long it takes to send a signal through that route which previously held sensitive data, begins to deviate immediately. After almost 200 hours, there's a 20 picosecond deviation between routes that hold a 0 value and routes that hold a 1 value. And that is the Pentimento beginning to emerge. Now, 10,000 picosecond routes is quite long. We again try this with 1,000 picosecond routes, and we see the same effect. It's just 1/10 as pronounced. So this can be done with realistic route lengths. So this is not enough to form an attack yet, because if you recall, the period where this initial bias is occurring is during the time period when the original user has access to the device and that sensitive data is still present on the board. What the attacker sees is just the very last data point in this plot. They don't know what the nominal timing behavior is. They don't have an hour 0 to compare against. But what the attacker can do is rely on the fact that the bias temperature instability is an elastic effect. And for example, if we invert the value in the sensitive routes in our local experiments, we begin to see that the delay through those routes that contain sensitive data begins to immediately return to its nominal timing behavior. And from that, an attacker can extract what the previous value was. All they have to do is apply ground to all the routes and study the recovery behavior. If the route previously held a 0 value and the attacker instantiates a 0 value into that route, then the timing behavior is going to remain the same. If that route previously held a VCC, high voltage value, and then the attacker instantiates a 0 value into it, they're going to see what this magenta plot shows, an immediate return to nominal timing behavior of the route. Now we're interested in turning towards the cloud with these local findings. There's many challenges with that. There's temperature fluctuations, voltage fluctuations, and the devices are significantly older, which is important to note because the bias temperature instability effect becomes less pronounced over years of use. Thank you very much.